All right, thanks everyone for being in this talk, and thanks to various organizers for inviting me. I would be talking about convex programming in small space. This is joint work with these suspects. I would not probably go into as much details as David, but more kind of explain the bigger picture ideas. And I have not put very specific references, and I'll be hanging out for a couple more days, so feel free to ask me questions about specifics of things which I would be talking about. Okay, so I was thinking about what talk would I give on a nexus of inference and computation. I thought long and hard, and I came up with this line. You may, of course, disagree with this completely or in part. But that being said, a lot of inference algorithms are solved by optimization. You reduce your problem to some optimization. And the situation is you have tons and tons of data points and measurements. But the classic issue where it connects to streaming algorithms is that your final answer, what you're looking for, is typically small. And if I were to give you that answer, that this is the answer, now verify this answer on this large set of data points, that's probably a far easier task. And you can see in all these streaming things which we're listening to, that if I actually gave you the heavy hitter, you can probably just keep its count or something like that, or find it from a sketch. The main question, what I'm interested in from the perspective of optimization, is how do we actually solve the optimization problem and space efficiently? And what bothers me is that a lot of these optimization problems, the constraints of the optimization problem are fixed or known in advance. And I'll give you two examples right in the next slide. Now then the question is, your constraints are fixed, you know your final answer is small, and your optimization process now takes these humongous amounts of space, and you're blowing up all kinds of parameters. So that's fundamentally bothersome as an optimization. Okay, so here's one example. I'll give you a couple of. So think of canonical combinatorial optimization problem. We are looking at a matching on an n vertex m edge graph. This is very different from perfect matching. The wij is the weight of the edge ij. Yij is whether you have selected it in the matching. This constraint is saying that if I add over all the neighbors of I pick at most one edge. And this is, I pick edges which is 0 or 1, which is relaxed to just greater than or equal to 0. You have seen this many, many, many times. This is the bipartite maximum matching. So what happens if I'm interested in the matching problem, which is the classic combinatorial example, is along with these vertex constraints, you get these odd set constraints. All it is saying is that if you have an odd set U, or if you have any set U, look at the total number of edges which belong to that set, just on the subgraph induced by that set. That's at most this function, the floor of U divided by 2. So if U were an even set, this says nothing. These inequalities would imply that. If U is an odd set, for example, if you have a triangle, you can pick at most one edge out of a triangle, because if you have 3 vertices, your matching size is at most 1. If you think of the wij's are 1. Okay, so think about the solution. Think about the matching solution which you're looking for. You're looking for at most order n edges. And let's see some pictures in terms of constraint matrices. If you think about whatever's on the left, I like seeing this as a picture. If you did not have these constraints, the total number of constraints here is n. So the constraint matrix looked like m by n. Why is it m? Because the number of variables is m. That's the number of edges. So your constraint matrix looked like this. Once you add the odd set constraints, you add this block of constraints. Keep in mind that if you look at the non-bipartite matching, the constraint matrix is m by 2 raised to order n, and your answer is smaller than the smaller side of this constraint matrix. So if I gave you the matching, you can verify that. But if you wanted to write this constraint matrix, it would be more than the size of your answer. You can ask what happens if instead of optimum solution, I want a 1 plus delta approximation. Well, you don't need to consider all these constraints. You can reduce this to n raised to 1 by delta. But it's still pretty large. Then you can ask that, hey, I have tons and tons of methods of solving maximum matching. Why would I want to solve this linear program? And that's a very fair question. The reason you may want to solve the linear program is if you can solve the linear program, all these extensions like capacities on vertices, capacities on edges, various forbidden sets, they come for free. Whereas if you try the standard Blossom contraction algorithm, you would have to devise a variant for each one of them. And in particular, Blossom contractions do not work when you have vertex and edge capacities, because then the Blossom it's an odd set with some antlers growing from the sides, and you cannot iterate over those structures easily. So this is one example. And here is another example. This problem is known as correlation clustering. Not many of you have seen. What this problem says is I have a graph. And I give edges weight. I give you a graph where these vertices correspond to some object, and the relationship between them correspond to some strength or affinity or something like that. And what you want to do is you want to partition this graph. For example, this would be a good partition. Let me give this would be a good partition. What you want to do is you want to preserve all the positive edges, and you want to cut all the negative edges. So in this example, this edge was minus 20, you certainly would want to cut it. And you would want to preserve the large positive edges, say the plus 10 and the plus 9 here. So you do not have a bound on the number of clusters, but what you have is you are looking for a partitioning of the graph, and you want to minimize the disagreements of the positive edges which are being cut and the negative edges which are not being cut. So this is a disagreement in this case, and that is a disagreement in this case, because you're cutting a positive edge and you're not cutting a negative edge. And you're not cutting this negative edge because keeping the rest of the chain, you get 8 plus 5 plus 9, which is a much larger number than minus 2. Good. This is used in a bunch of different learning tasks. How does one formulate this as an optimization problem? The classic formulation, this was introduced by Blum et al. About 2004. You have variables yi, j, which correspond to does I and j belong to different sides of the cut or the same side of the cut. So yij equal to 1 means you're cutting I and j. Yij equal to 0 means you're not cutting I and j. So now if you look back, yij equal to 1, and you're cutting I and j have a positive weight, that goes to your objective function. That's a bad thing. If yij is 0, then this doesn't contribute anything to your objective function. On the other side, if yij is 0, that means you're not cutting this edge, and it's a negative edge, then that's a penalty for you. At the same time, if yij is 1, then you're cutting this edge, and it's a negative edge, and you don't care. So that's the objective function. Now, how do you represent a cut? It's very simple. If you look at every triple, I, j, and k, the constraint you will write is, if I am cutting I and k, so the way to read this constraint is, if I separate I and k, for any other point j, I must have j either with I or with k, or in a yet third cut. In all cases, at least one of these should be 1 if this one is 1. So these are known as triangle constraints. So it's a very nice way of representing cuts. In a picture, all this is saying is if I have this thing, if I have I and k cut, the cut should either go this way or that way. You have to cut the other two, one of the other two. So this is an optimization problem. And if you think about the structure of constraints, you know these constraints. It's n-cube constraints. There's no information in the constraints. The entire information is in the objective function. Think about that for a second. So the constraint matrix is completely specified to you. So now my question is, you have this size optimization problem. What is the size of your final answer? Your final answer is a partition. You're just partitioning the vertices. If you just tell me vertex 1 goes to partition 1, vertex 2 goes to partition 2, it's O of n space. So once again, you're trying to solve this linear program, and the answer can be specified implicitly using linear space, linear in the number of vertices. So this is the starting point of why we may want to do something interesting. Sure. You can, yeah, so that's several slides ahead. However, what would happen is you would still need a lot of constraints.
It's only one of you. Just say on every node, I decide which cluster it belongs to.
So are you assuming there are just 2 clusters?
You can have more than 2.
We can have more than 2 clusters here. And imagine, even if you have 1 or 0, you still need to give me a notion of cut.
The cut is just
I see. Very good. I get. So 0 and 1 would work for integer programming. Now, how would you express that as a feasible linear relaxation? You may get everything as half then, and that may not be so interesting. We can take this offline, because you will change this to yi minus yj, and I'll say everything is a half. If you don't have constraints, and if I don't have integrality, that relaxation may not preserve what you're trying to capture. Okay. So this is another example where the answer is very small, but so far, the best known method of solving this problem has been to solve this matrix, solve this linear programming relaxation. And the approximation factor you get out of this is log n. This is a result. This was in the original Blum et al. Paper. Okay, so quick. So I'll go through a bunch of tools which we will use. So the first tool is the multiplicative weights method. Many of you have seen this in learning algorithms. Who has seen this before? Okay, so let's talk about this quickly. There's a few pictures. So you want to solve this linear program. AY is less than or equal to B. C transpose Y is greater than or equal to beta. Y is greater than or equal to 0. If you think about this, this is the exact form of the maximum matching constraints, and no surprise that it's written like that. So what you want to do is you want to find a feasible solution Y in this space. You don't know what this space is because you haven't solved the particular constraints yet. Now suppose you view of this, that I view the optimization that I want to find a feasible point in this space, but I can encompass this hard space into some easy to optimize space, a very large space. One way of thinking is I can easily find points here. I'd have to work a lot harder to find a point there. And the way we will look at the easy space is of the following form, that you will blow up some of the constraints by this factor, which is known as width. Now, what I will do is the following. I will give you hyperplanes, which will correspond to assigning some weights to the set of constraints. And I will ask you the following question is, you don't have to find a point in this hard space. That's a hard optimization. You don't have to solve that. I give you this hyperplane. Give me a point which is on the same side as the space you're looking for. So if this is my hyperplane, give me a point which is on the left. And if you had one here, that's exactly separating the space, I even let you have some relaxation of this. All this is saying is I kind of look at my hard constraints. I give you a bunch of weights, find something which satisfies the constraints on the average. That's all that is being said. So you satisfy this, and this has been known for a very long time, since about 89, Littlestone, Warmoth, and there's a lot of results after that. So suppose you gave me that point over there. What I would do at this point is I would change these weights u, and I'd give you another hyperplane. And you'd give me that point, and I'd change the hyperplane, and you'd probably give me this point. And you're already seeing what I'm doing is as my hyperplanes are changing, I'm kind of scoping out, ruling out that which side the feasible space is not there. So I play this game for a few times, and what I do in the end is very simple. I just average all the points which you have given me. So I just take all these black dots, get this red dot, and that's it. That's my algorithm. It's not my algorithm, that's the algorithm of Littlestone-Warmoth. All right. What can you guarantee? What you can guarantee is that if you were looking for ay less than equal to b, you end up getting something which is ay is less than equal to 1 plus epsilon times b. And if you are looking for C transpose y is greater than something, you get a relaxation there. So in the sense that if this was your hard polytope, you kind of are in the neighborhood of that polytope. So that's a fascinating thing. I never really tried to solve this hard optimization problem. I kind of solved the easy optimization problem a bunch of times. And when I average it, I've solved my hard problem, which is fascinating. The number of iterations of this procedure depends on rho, epsilon, and the update mechanism of u. One easy way of analyzing is this formula. It's order rho square by epsilon square, where rho is the extent of that easy polytope, epsilon is a guarantee you're looking at, and the whole analysis is done by a potential function. It's log of the initial potential divided by the final potential. It's standard. You could think of it as rho square divided by epsilon square times log of n, where n is the number of variables. So how does one use this in multiplicative weight update method for matching? This is the only proof which I'll give because it's pretty simple to show this without much effort. This is a problem which I want to solve. So let's look at it in the matrix form. I have n constraints for the variables. I have m variables. What I'm going to do is I'm going to maintain these bunch of weights, one for each row, which are the weights on the vertices at this point. This is my vector u, which was referred in the previous slides. And I have a shadow matrix, which is the easy polytope to solve. And instead of solving this optimization problem, I would multiply this by this set of weights. So this becomes just one single constraint. And I'll replace these hard constraints by something which is easier. So let's see an example of that in a sec. So, all right. So that was the matching polytope. So think about multiplying all of these by weights xi and adding them up. You're going to get that. I haven't done anything. This is that you want to preserve your objective function. Here it was a maximization. I just made it a decision version. I haven't done anything else. So you want a large matching. You want these constraints to be true on the average. That means the average degree is at most 1. This is your easy polytope. Here you had 1. You have relaxed that by rho, which means intuitively means that can you solve your maximum matching even if I let you relax the degree of a vertex from 1 to something rho? That's a question there. So this is a problem which you want to solve. An easy transformation of the top inequality is that instead of multiplying by xi and taking the sum over I can sum it over the edges, and it's the yij times this. I haven't done anything yet. Now, if you look at this, I have these two constraints and this easy set of constraints, which I've been calling. I'll not give a proof of this, but believe me that suppose for any given lambda, any positive lambda, if I can solve a linear combination of these two constraints along with these constraints, then I can solve this optimization problem. It's not very hard to believe. You just have to do the algebra a little bit. So this was, say, constraint 1, constraint 2. I just solve a linear combination of those constraints. So let's write the linear combination of constraints, multiply that by lambda, and subtract it from this thing. So the constraint looks like this. And this constraint follows from here. I kept the other constraint. So question about what is a basic step which I need to solve in the optimization problem? Done? Are we good? Okay. Now, so I haven't changed anything yet other than this was sum over yj wij. This is sum over ij yij. Oh, this should have been just yij. This sum over this yij and this yij are the same, so I just collect all those together. This is what I want to solve. Now think about for a second, if you had a feasible maximum matching of size beta, what must have had happened? The feasible maximum matching would have solved the first constraint, would have had 1 here, and would have had these things as greater than or equal to 0. Okay? If your original problem were feasible, you would have a solution where rho is equal to 1. Okay? Now, let's do the following. Suppose I say that do not solve maximum matching, but give me an approximation algorithm which gives me 1 by c for some constant c, let even be 10. So if you have a large matching in your graph, give me 1/10 of the size of matching. Why can I say that? If you look at this optimization, all I'm doing is I have these original weight functions ij. I'm just subtracting lambda times xi and lambda times xj. It's in the sense that I'm adjusting the weight of each edge. And the weight is contributed, the adjustment of an edge is contributed from both sides. So suppose you gave me a C approximation. Think of C as 10 or 20 or 200, doesn't matter. If you give me a maximum matching, which is 1 by 200 approximation, then you would be giving me a solution of this problem. Are we? All right. You give me a solution to this. Here's a trivial thing which I can do. I take every yij and I multiply it by c. That's it. If I multiply everything throughout by c, I would satisfy this thing with a factor of c, and I would get that. This thing will get multiplied by c, and I'll get that, and I've solved my optimization problem, or subproblem. So what happened? All that happened is when I apply multiplicative weight update to the bipartite matching case, I have proved to you if you have a constant factor approximation, that's the oracle you need to repeat over and over again. And once you average these approximation solutions, you will get your final fractional solution. And keep in mind, any constant really is fine. So say p equal to 10 or 20, the number of iterations doesn't change as long as rho is a constant. It's just whether if you have a bad approximation, you'll converge slowly. If you have a good approximation, you'll converge much faster. Keep in mind, the final solution will be a 1 minus epsilon approximation. So even though at each step you're getting a constant factor approximation, your final answer is a 1 minus epsilon approximation. So if you have, so the question at this point is, what is the insight? How can I solve this maximum matching problem? Think about the edges are going to be given to you one at a time. That is, this is my maximum matching problem. I'm revealing the columns of this one at a time. I can run an easy online approximation algorithm to kind of solve this. What the online approximation algorithm, and this is one interesting insight to keep in mind, even if you've seen this before, what the online approximation algorithm is doing at each point of time is filtering the columns based on the constraint. Is the weight, the adjusted weight of that edge, positive or negative? That's this optimization problem, which means I have an edge. I have this edge. This thing contributes minus lambda xi. This thing contributes minus lambda xj. Even after adding up all the contribution, is that edge still relevant to me? If this is not true, that will never appear as a auxiliary problem which you want to solve. So what the algorithm is really doing, you're assigning weights to vertices, and you're filtering out the edges, and you're finding approximation solutions in this. And you're repeating a collection of this. So questions about this before? And this is actually all you just need this, and you just already have a result that 1 by epsilon square log n passes over, or log n collection of maximum matchings is sufficient. Okay, now another way of thinking about it is you are using the maximum matching over the large violations, but we'll come back to that later. In fact, in the maximal matching, you only would be interested in the large values of this thing. You will ignore the small values of that. Okay, so you should ask me, we kind of alluded to this. This is the optimization. This was my easy shadow polytope. I had reduced that to one constraint. All I said is I need to store n numbers, and this whole thing becomes one equation. So my total storage space is actually n. If you are a streaming aficionado, this is not a one-pass algorithm. Let's move on. Now let's think about the classic combinatorial optimization problem. The real big kahuna, the beautiful problem of matching is typically non-bipartite matching. So I can try to apply the same thing. But now, if you think about it in terms of picture, earlier I was remembering only n values. But now if I give weights to all these constraints, I have to remember n raised to 1 by delta values. That's a bit much. So this is not going to work. I'm going to claim something without a proof. What is fascinating is, and that's the intuition that I look at the violations, if instead of storing all these weights, if I just store the largest weights, that's enough for the algorithm actually. One intuitive proof of that is how many of you are familiar with the ellipsoid algorithm? So in the ellipsoid algorithm, again, in a situation like this, you want to satisfy a whole lot of constraints. The oracle which you have to solve at each point of time, one oracle, is give me the maximum violated constraint, even though there are exponentially many, which corresponds to, instead of storing all these weights, you just pick the maximum weight here. If you were just storing one maximum weight, you would get ellipsoid. Now, ellipsoid converges slowly, and we know that. The proof really follows the fact that instead of storing one maximum weight, if you stored a bunch of weight, what happens to the convergence? And the equations kind of work out. And this is the proof by the picture. You kind of maintain the weights on the large odd sets. These are the densest odd sets. If you remember the traditional algorithm, these would be your blossoms. You're right, choosing a set of blossoms. And you basically, again, get a solution of non-bipartite matching with capacities, and the running time is linear in M, and the space is almost linear in N. And this is probably, as far as I know, this is one of the first algorithms which are strongly polynomial in BI and CIG. If those numbers were very large, this algorithm will still be strongly polynomial time, but you'd only get an approximation, of course. Again, for streaming aficionados, the number of iterations goes up, but it's so tilde of some constant, which is your approximation. Okay. Now, I want to go back slowly to the correlation clustering, and even if you have seen talks like this, the similar talk like this, the key insight here is in correlation clustering, the Yij followed from a partition expressed in O of n space. This is what you were also alluding to. So I was really interested in this partitioning. Yij was one way of expressing that partitioning. So can you think of a similar implicit solution for matching? What would that be if I asked the same question for matching? One way is, in all implicit such things, is you should think about the dual. What the dual is saying that give me a collection of edges and there are no dense regions in the graph. And that view is a view of partitioning. And so that's the dual. So this was the large matching instance which I was trying to solve with non-bipartite constraints. The position I'm taking that would you rather be solving matrices which look like this or which look like that? Why would you care about this? This is a lot more variables, so there are a lot more degrees of freedom. Satisfying constraints here is significantly easier than having so many constraints to be satisfied. So the solution will be to apply multiplicative weight update to the dual. The only caveat is multiplicative weight update needs an easy shadow polytope. And if you think about the primal space, you're not solving the problem anymore. That's a problem of applying multiplicative weight update method to the dual and saying I've solved my primal. You have not solved your primal, you've solved this weird object, which is a primal plus a whole bunch of other things. So you can use multiplicative weight update, but you have to be careful. The intuition is, if you remember what these column constraints were, the remark which I had made that I only looked at large violations. So when you do not make progress on the dual, all your columns have small violations, right? And if you now go back in the primal space, that means all your constraints are almost satisfied. You have to argue that, but you can. And this is where the insight that these were based on the violations were important. And so the entire proof, the algebra does work out. It's not very intricate, which becomes that either your multiplicative weight update will progress on the dual, or you'll have a direct one-step solution of your primal. And that one step is necessary because otherwise you'll be solving a very strange function. So this is interesting to me because it's a primal dual approximation and primal dual LP solution. If you're not an approximation algorithms aficionado, this may not be of interest to you. Okay, so at this point, you should be asking me this question that whatever I told to you should not work, because what I said, this is your constraint matrix, this is your shadow matrix, I need to remember those weights. But now I'm remembering M weights remember M was the weight, M was the number of edges in your graph. I have not saved anything. I'm remembering all the edges, so this may not be the best space efficient way. So I've really not given you any space savings yet. So the solution to that, and that has been the theme of this entire kind of set of talks in the last 2 days, is instead of thinking of the weights being stored explicitly, just think of the weights being generated through some kind of a pseudo-random matrices. In particular, the matrices we'll use are cut sparsifiers. Instead of storing m weights, I will be able to compress them into order n weights and generate these m weights from those n. And again, we have to kind of work this through. Because of the structure of matching polytope, this way of generating or this way of compressing the m weights into n weights is sufficient. That depends on the structure of the polytope, but that works out in this case. You still should have a following question, that how do I solve the shadow matrix? And this is where it becomes more interesting. So there are 2 ways you can do it. One is just forget the shadow matrix, solve one constraint at a time. That was similar to the ellipsoid. You will pay in the running time, but your space would be smaller. Or you show that you do not need such a large shadow matrix. Storing some bunch of the matrix is sufficient, and then you need to remember only these n numbers corresponding to this dimension. For the maximum non-bipartite matching, the picture that gives you the algorithm is this. These are the shadow constraints on the vertices. They are sufficient to give you the shadow constraints on the odd sets. So in the last couple minutes, let me show you how does this thing apply to correlation clustering. So this is the linear program which you saw about correlation clustering. I haven't changed that. I'm now going to change that relaxation to a different relaxation. What this relaxation would be, it's the same objective function. However, instead of expressing a cut over triangle constraints, I would express a cut over cycle constraints. One way of seeing a cut is, imagine this is an edge and I haven't cut it. Imagine this is an edge and I haven't cut it. Imagine this is an edge, I haven't cut it. Imagine this is an edge, I haven't cut it. And then I say that I have cut this edge. So that's not fair, right? If I give you a cycle and you have cut this edge, you have to cut the edge somewhere else. So these are the constraints I would write, except these squiggly lines would be over the negative edges, and these straight lines will be over the positive edges. All we would say is take any path from S to T over the positive edges. If you have cut the negative edge, if YST is 1, then over the path of the positive edges, you must have cut. If this is 1, you must have cut the edge somewhere here. It's a generalization of the triangle to larger cycles, actually. Good? So if this is the objective function, at this point you should say that, hey, this is a big bluff. I originally had a matrix which had m variables and n cube constraints. I just told you that try this relaxation in which number of variables are the same, but number of constraints is for all edges and for all sets of paths. This should be for all edges and for all paths. So the number of constraints have become now exponential. This is a terrible idea in general. But again, since the solution is implicit, I'm going to try that instead of solving this constraint matrix, I'm going to try to solve its dual. What happens is I was writing constraint over paths. If you think about its dual, duals of paths are cuts. So the dual is now over cut metrics, and we have technology to use sketches over cuts, which is the cut sparsifiers. So I can solve this optimally and efficiently. Once again, what I would get is a violation here. And in one step, I would show that if all these violations are small, this violation is small. So let's look at what these constraints are. These constraints came from these constraints, which are of this following form, that if I look at a path, they are mostly equal. Now, this is the picture here. Look at its contribution from the objective function. Think about in your fractional solution, if you had given, if this path from S to T was already of length half, or length, I can double each of these lengths, or one other way of saying is, suppose YST was greater than 1/3, I can actually multiply it by 3 and just cut this edge. I'm already paying for it. Sorry. Suppose YST was less than 1/3, I am already paying for it in the objective function, which is at least 2/3. So I can actually, if YST is less than 1/3, I can simply send YST to 0. My objective function would not change. So if I do this transformation, my rest of the feasible solution is the following form. It's an embedding where the distance between S and T is greater than 1/3 for every pair of S and T. Okay? Otherwise, I have an easy solution for the remainder of the variables using this. This problem, the fact that I give you an embedding in which terminal pairs or pairs of vertices are far apart, in this my notion of far is 1/3, is known as the classic multi-commodity flow problem. So once you get a solution like this, apply your multi-commodity flow approximation algorithm, and you're done. So the entire trick was to use sketches and to get to these Yij values, which are represented in the sketch form. And that's pretty much the entire proof of the correlation clustering. If you're interested, I can show you the details offline. And something happened here. And that's pretty much what I wanted to talk about. So okay. I think even my laptop has given up on this. So that's pretty much all I wanted to talk about. So questions? Great. So in the basic matching problem, the edges come one at a time, but the columns correspond to the edges because the columns correspond to the variables, and my variables corresponded to the edges. So in the first example which we saw, which is, let me go back. Yeah, so even here, so the variables corresponded to the Yij. So in a connection to a streaming algorithm, your constraint matrix is fixed, and I'm giving you one column of the constraint matrix at a time. And so because the number of rows is n, I just need to store these weights, and once you give me a column, I can do all the n operations needed to update this entire matrix. And it also helps, of course, that for an edge, in a because these correspond to edges, there are at most 2 non-zero entries in this column. If that were not true, I would be doing a lot of work. So,
use other relaxation, like Henri Adams last year. Do they also have a view on this?
yes, so one way, and the view of the relaxations is, so bipartite matching is a really easy problem. I mean, it really fits in 2 slides. So for bipartite matching, I don't think they would say anything interesting. But you can think of all the different hierarchies in the non-bipartite matching. So your lifting process can be that I first would introduce all constraints corresponding to triangles. Then I'd introduce all constraints corresponding to 5 cycles. So that's a very natural view. In a sort of algorithms literature, I think Claire Mathieu, and I'm blanking on her co-author's name, they had a paper, I think 5 years back, showing that for non-bipartite matching, there's a way of viewing these hierarchies and getting this answer. But the corresponding thing is I'd introduce these constraints, all triangle constraints, solve the problem, introduce all 5 cycles in this kind of form. So here, actually, you can do that in a streaming fashion. That would still be fine because the number of sets of constraints you would have to introduce is order 1 by delta, because you will only need to go up to subsets of size at most 1 by delta. So you can think of first you introduce all the triangle constraints, then all the degree 5 constraints, and so on and so forth.